of today's module is Ring of Matrices. Dear learners, today we are going to learn about Ring of Matrices. Let us see some basic concepts related to matrix. In mathematics, a matrix is a rectangular array of numbers, symbols or expressions arranged in rows and columns. For example, the dimensions of the matrix below are 2 by 3 because there are 2 rows and 3 columns. 1, 6, 7, 2, 4, 9 is 2 by 3 matrix. Provided that they have the same size, each matrix has the same number of rows and the same number of columns as the other. Two matrices can be added or subtracted element by an element. The rule for matrix multiplication, however, is that two matrices can be multiplied only when the number of columns in the first equals to the number of rows in the second. That is, the inner dimensions are the same n for an m by n matrix times an n by p matrix resulting in an m by p matrix. There is no product the other way round. A first hint that matrix multiplication is not commutative. Any matrix can be multiplied element-wise by a scalar from its associated field. The individual items in a m by n matrix A often denoted by aij, where I and j usually vary from 1 to m and n respectively, are called its elements or entries. For conveniently expressing an element of the results of matrix operations, the indices of the element are often attached to the parenthesized or bracketed matrix expression. For example, ABIJ refers to an element of a matrix product. See this m by n matrix. It's having n columns and m rows. The vertical arrangement is called as columns. The horizontal arrangement is called as rows. See this matrix A11, A12, A13 and so on A1n. The next one is A21, A22, A23 and so on A2n. This is rows. The last one is AM1, AM2, AM3 and so on AMN. Which one is column here? Yes, you are right. A11, A21, A31 and so on AM1 is called as the column here. In abstract algebra, a matrix ring is any collection of matrices forming a ring under matrix addition and matrix multiplication. The set of n cross n matrices with entries from another ring is a matrix ring, as well as some subsets of infinite matrices which form infinite matrix rings. Any subrings of these matrix rings are also called as matrix rings. In this case, when R is a commutative ring, then the matrix ring Mn of R is an associative algebra which may be called as matrix algebra. In this situation, if M is a matrix and R is an R, then the matrix Mr is the matrix M with each of its entries multiplied by R. Let us see the ring of n by n matrices. Recall from the rings introduction module that if plus and star are binary operations on the set R, then R is called ring under plus and star. It's denoted as R, plus, star when the following are satisfied. For all A, B in R, we have that A plus B in R is closure under plus. For all A, B, C in R, A plus B plus C is equal to A plus B plus C. Associativity of elements in R under plus. There exists A0 in R such that for all A in R, we have that A plus 0 is equal to A and 0 plus A is equal to A. the existence of an identity element 0 of or under plus. For all A in R, there exists A minus A in R such that A plus minus A is equal to 0 and minus A plus A is equal to 0. The existence of inverse for each element in R under addition. For all A comma B in R, we have that A plus B is equal to B plus A. Commutativity of element in R under addition. For all A comma B in R, we have that A star B is equal to B star A, closure under star. For all A comma B comma C in R, A star B star C is equal to A star B star C. Associativity of elements in R under star. There exists an element 1 in R such that for all A in R, we have that A star 1 is equal to A and 1 star A is equal to A. The existence of an identity element 1 of R under star. For all A comma B comma C in R, we have that A star B plus C is equal to A star B plus B star C and A plus B star C is equal to A star C plus B star C. Distributivity of star over plus. Let us verify that the n by n matrices form a ring or not. Let Mn denotes the set of n by n matrices and let plus be the operation of standard matrix addition and let star be the operation of standard square matrix multiplication. Let A comma B comma C in Mn. We know that from linear algebra, the sum of two n by n matrices is an n by n matrices, so Mn is clearly closed under plus. Furthermore, matrix addition is associative since A plus B plus C. Here we will take the matrix A as A11, A12 and so on A1n. Like this, AN1, AN2 and so on ANN. Next, we will take the matrix B as B11, B12 and so on B1n and BN1, BN2 and so on BNN. The next C matrix, as you try, write C11, C12 and so on C1n and CN1, CN2 and so on CNN. Now, we are going to add B plus C. So, the result will be, already we are having A as like as it will be there. So, A11, A12 and so on A1n, AN1, AN2 and so on ANN. Now, we are going to add B plus C. The result is B11 plus C11, B12 plus C12 and so on B1n plus C1n, like BN1 plus CN1, BN2 plus CN2 and so on BNN plus CNN. Now, we will add B plus C with A. So, the result is A11 plus B11 plus C11, A12 plus B12 plus C12, like A1n plus B1n plus C1n, like AN1 plus BN1 plus CN1, AN2 plus BN2 plus CN2 and so on ANN plus BNN plus CNN. Now, all the elements are in ring. So, it will satisfy the associative property. We will exchange it. So, how it will be written? A11 plus B11 plus C11, A12 plus B12 plus C12 and so on A1n plus B1n plus C1n, like AN1 plus BN1 plus CN1 and so on ANN plus BNN plus CNN. Now, we are going to separate C. So, it will be written as A11 plus B11, A12 plus B12 and so on A1n plus B1n. Like this, AN1 plus BN1, AN2 plus BN2 and so on ANN plus BNN. Now, we have separated the C. So, the C will be written as C11, C12 and so on C1n, like Cn1, Cn2 and so on Cnn. Now again we will separate A and B. So it will be written as A11, A12 and so on A1n, AN1, AN2 and so on ANN plus B11, B12 and so on B1n. Like this Bn1, Bn2 and so on Bnn. Plus already C is separated. So C11, C12 and so on C1n. Like Cn1, Cn2 and so on Cnn. So what is the result now we get? A plus B plus C. Thus A plus B plus C is equal to A plus B plus C. The identity element of plus is the n by n 0 matrix. 0 is equal to 0, 0, 0, 0 and 0, 0, 0, 0. It's in columns and rows we are having only zeros. Since A plus 0 is equal to, already we have seen A is the n by n matrix. It's having the rows and columns like this. A11, A12, A13 and so on A1n. Like AN1, AN2 and so on ANN. Already we are having the 0 matrix is plus 0, 0, 0 plus 0, 0, 0. So the answer is A11 plus 0, A12 plus 0 and so on A1 plus 0. Like AN1 plus 0, AN2 plus 0 and so on ANN plus 0. So it's equal to A11, A12 and so on A1n, like AN1, AN2 and so on ANN, which is again A. So A plus 0 is equal to, yes, A. Similarly, it can be shown rather easily that 0 plus A is equal to A. For each n by n matrix, the additive inverse minus A is, since A plus minus A is equal to, the A is A11, A12 and so on A1n, and like this AN1, AN2 and so on ANN. Here the matrix is minus A, it will be written as minus A11, minus A12 and so on minus A1n. Like this minus AN1, minus AN2 and so on minus ANN. So the result will be A11 minus A11, A12 minus A12 and so on A1n minus A1n. Like this AN1 minus AN1, AN2 minus AN2 and so on ANN minus ANN. So what's the result may be? You are right, is 0, 0, 0. Once again, it can also be shown that minus A plus A is equal to 0. The operation plus of matrix addition is also commutative, since A plus B is equal to A11, A12 and so on A1n, like AN1, AN2, AN3 and so on ANN. And again the B matrices plus B11, B12 and so on B1n, like Bn1, Bn2 and so on Bnn. Now we are going to add A plus B. So the result will be A11 plus B11, A12 plus B12 and so on A1n plus B1n, like AN1 plus Bn1, AN2 plus Bn2 and so on ANN plus Bnn. We will use the commutative property here. So we will get the result as B11 plus A11, B12 plus A12 and so on B1n plus A1n, like Bn1 plus An1, Bn2 plus An2, like Bnn plus Ann. Again we will separate it. We will get the matrices B11, B12, B13 and so on B1n, like Bn1, Bn2, Bn3 and so on Bnn. This is the matrix B, and we will get the matrix A as A11, A12, A13 and so on A1n, like AN1, AN2 and so on ANN. It will be written as B plus A. So A plus B is equal to B plus A. We know from linear algebra that M by N matrix can be multiplied by a N by R matrix to produce a M by R matrix. Therefore, a N by N matrix multiplied by a N by N matrix will produce a N by N matrix. So, Mn is closed under star. Showing Mn is associative is rather tedious though it can be done, we will omit it here. The identity element for multiplication of matrices in Mn is the n by n identity matrix In. Lastly, it can be shown that the distributivity property also holds, but once again it's rather cumbersome, so we leave it to the readers to verify. Therefore, Mn under addition and multiplication is a ring. Let us see the example. The set R of all matrices of the form AB minus BA, where A, B in R is a ring under matrix addition and matrix multiplication. Let us prove this. Let A is equal to 2 by 2 matrix AB minus BA and B is also 2 by 2 matrix CD minus DC in R. Then A plus B is equal to, now we will add this, AB minus BA plus CD minus DC. So, is equal to A plus C, B plus D minus B plus D, A plus C in R. And now we see AB, we will multiply it. So, AB minus BA, CD minus DC. While we are multiplying, we will get the answer as AC minus BD, AD plus BC minus AD plus AC, AC minus BD in R. Clearly, matrix addition is commutative and associative. Here, 0, 0, 0, 0 in R is the 0 element and minus A minus B, D minus A is the inverse of the matrix, is equal to AB minus BA in R. Further, matrix multiplication is associative and the distributive laws are valid for 2 by 2 matrices. Therefore, R under addition and multiplication form a ring. Similarly, the set of all matrices of the form A0, 0, 0, where A in R is a ring under matrix addition and multiplication. The set of all matrices of the form A0, 0B, where A in Z is a ring under matrix addition and multiplication. The set of 2 by 2 matrices with even integer entries form a ring under matrix addition and multiplication. Now let us see some definitions. Definition of simple ring. A simple ring is a non-zero ring that has no two-sided ideal besides the zero ideal and itself. A simple ring can always be considered as a simple algebra. Rings which are simple as rings but not as modules do exist. The full matrix ring over a field does not have any non-trivial ideals, since any ideal of Mn of R is of the form Mn of I, with I is an ideal of R, but has non-trivial left ideals, namely the sets of matrices which have some fixed zero columns. According to the Artin-Wedderburn theorem, every simple ring that is left or right Artinian is a matrix ring over a division ring. In particular, the only simple rings that are a finite dimensional vector space over the real numbers or rings of matrices over either real numbers, complex numbers or quaternions. The next definition is for normed ring. A vector space with a ring structure and a vector norm such that for all v, w in V, norm of VW is less than or equal to norm of V dot norm of W. If V has a multiplicative identity 1, it is also required that norm of 1 is equal to 1. The field of real number R is a normed ring with respect to the absolute value, and the field of complex numbers C is a normed ring with respect to the modulus. In both cases, the above inequality is actually an equality. More general examples are the ring of real square matrices with the matrix norm and the ring of real polynomials with the polynomial norm. Let us see some structure of matrices. The matrix ring Mn of R can be identified with the ring of endomorphism of free or modulo of rank n Mn of R is isomorphic to endomorphism of Rn over R. The procedure for matrix multiplication can be traced back to compositions of endomorphism in this endomorphism ring. The ring Mn of D over a division ring D is an Artinian simple ring, a special type of semi-simple ring. The ring's column finite matrices of R over I and row finite matrices of R over I are not simple and not Artinian if the set I is infinite. However, they are still full linear rings. In general, every semi-simple ring is isomorphic to a finite direct product of full matrix rings over division rings, which may have differing division rings and differing sizes. This classification is given by the Artin-Wedderburn theorem. There is a one-to-one correspondence between the two-sided ideals of Mn of R and the two-sided ideals of R. Namely, for each ideal I of R, the set of all n by n matrices with entries in I is an ideal of Mn of R, and each ideal of Mn of R arises in this way. This implies that Mn of R is simple if and only if R is simple. For n is greater than or equal to 2, not every left ideal or right ideal of Mn of R arises by the previous construction from a left ideal or a right ideal in R. For example, the set of matrices whose columns with indices 2 through n are all 0 forms a left ideal in Mn of R. The previous ideal correspondence actually arises from the fact that the rings R and Mn of R are Morito equivalent. Roughly speaking, this means that the category of left R modules and the category of left Mn of R modules are very similar. Because of this, there is a natural bijective correspondence between the isomorphism classes of the left R modules and the left MNR of modules, and between the isomorphism classes of the left ideals of R and Mn of R identical statements hold for right modules and right ideals. Finally, let us see some properties of ring of matrices. The matrix ring Mn of R is commutative if and only if n is equal to 1 and R is commutative. If R is non-trivial and n is greater than or equal to 2, then Mn of R is non-commutative. Hence, Mn of R is non-commutative. For n is greater than or equal to 2, the matrix ring Mn of R has 0 divisors. An example in 2 by 2 matrices would be 0 1 0 0 1 0 0 0 is equal to 0 0 0 0. The center of a matrix ring over a ring R consists of the matrices which are scalar multiples of the identity matrix, where the scalar belongs to the center of R. In linear algebra, it is noted that ever a field F, Mn of F has the property that for any two matrices A and B, AB is equal to 1 implies BA is equal to 1. This is not true for every ring R though. A ring R whose matrix rings all have the mentioned property is known as a stably finite ring or sometimes weakly finite ring. The set of all n by n matrices over an arbitrary ring are denoted by Mn of R. This is usually referred to as the full ring of n by n matrices. These matrices represent endomorphisms of the free module Rn. The set of all upper for set of all lower triangular matrices over a ring. If R is any ring with unity, then the ring of endomorphism of M is a direct sum of R over I. As a right R module is isomorphic to the ring of column finite matrices of R over I, whose entries are indexed by I by I, and whose columns each contain only finitely many non-zero entries. The endomorphisms of M considered as a left-over module result in an analog object. The row finite matrices of R over I, whose rows each only have finitely many non-zero entries. If it is a normed ring, then the condition of row or column finiteness in the previous point can be relaxed. With the norm in place, absolutely convergent series can be used instead of finite sums. For example, the matrices whose column sums are absolutely convergent sequences form a ring. Analogously, of course, the matrices whose row sums are absolutely convergent series also form a ring. This idea can be used to represent operators on Hilbert spaces. For example, the intersection of the row and column finite matrix rings also forms a ring, which can be denoted by RCFMI of R. The algebra M2 of R of 2 by 2 matrix, it's a real matrix, is a simple example of a non-commutative associative algebra. Like the quaternions, it has dimensions 4 over R, but unlike the quaternions, it has 0 divisors, as can be seen from the following product of the matrix units. E11, E21 is equal to 0, hence it is not a division ring. It is invertible elements or non-singular matrices and they form a group, the general linear group ZL of 2, R. If R is commutative, the matrix ring has a structure of A star algebra over R, where the involution star on Mn of R is the matrix transposition. Complex matrix algebra as Mn of C are up to isomorphism, the only simple associative algebras over the field C of complex numbers. For n is equal to the matrix algebra, Mn of C plays an important role in the theory of angular momentum. It has an alternative basis given by the identity matrix and the 3 Pauli matrices. Mn of C was the sum of early abstract algebra in the form of biquaternions. A matrix ring over field is a Frobenius algebra with Frobenius form given by the trace of the product sigma A, B is equal to trace of AB. Okay learners, we have come to the conclusion part of today's module. Up to now, we have described about matrix rings. We started this module with basic concepts of matrix like matrix addition and multiplication. By using these operations, we have proved it forms a ring. But then we saw some definitions related to matrix ring. Finally, we discussed some of its properties. So, I hope you have learned from this session. Thank you.